Hey there, physics students. Welcome back to another edition of Rapid Review for Honors Physics. Today the topic is work, power, and energy. So let's get right down to it. So you may recall that work is done when a force causes a displacement. In fact, perhaps in middle school you might have learned force times distance. We are a little more sophisticated here now in our class because we have the power of vectors and trigonometry, and we realize you only get partial credit if you push something over a distance. And the way you calculate that partial credit is you look for the component that is parallel to the displacement. Let's break it down. Okay, so work is defined as force times distance times cosine of theta, where theta is the angle in between the force vector and the displacement vector. Notice that we're talking about two vectors, force and displacement, but we're calculating a scalar for that. So if you look how the equation works, the way you take into account the angle part of force and displacement is you look for the angle between them. That's what the theta is, right? So theta is the angle in between. Let me make sure I get this right. Here we go, the angle in between. So you end up with work, which is a scalar, and you are creating it by multiplying two vectors together. Notice how you're just taking the magnitude part of the two vectors when you do the multiplication. Looking across the bottom in units, as I always like to do, the work, W, by the way, that W means work, it's not weight, like I've used W for in the past. In context, I think you'll realize what we're talking about. I don't think there's too much of a risk of confusion. So next is the force, of course, is in newtons, and the distance ought to be in meters. When you're done, you get joules for your units. So if you think about angles, right, what kinds of things could happen if we have different kinds of angles, and what does that cosine theta do? If you take a few examples here, if theta is 0 degrees, you get full credit, force times distance. If theta is, let me pick something easy, 60 degrees, it's easy because its cosine happens to be 0.5, which is easy to talk about. We see that the work is force times the displacement magnitude, which is the distance the object moved, times 0.5. And then if you take it to an extreme and you go to 90 degrees, you'll see, of course, no work is done at all. So often you'll be asked, if a force is this way and the displacement is that way, what work is done? And then you'll know now the answer is 0, because there is no component in the same direction the thing is moving. Okay, power, I will now define the amount of work done per unit time. Another way to say it is just a rate, the rate at which work is done. So here's the calculation, nothing too fancy, and it's pretty easy to break that down. Power is a scalar, and if you put in your work in joules and you put in your time in seconds, you will get units of watts in your answer. Oh, great. There's that W again. Again, I think I found just from context, most students are not confused by that. Just, it's like W is work and W is watts. It's just the way it is. One's a quantity, work, and the other is units, watts, which is a unit of power. Okay? And also, while we're on the topic of units, take a look at the lower left corner of this slide. 1 watt is 1 joule per second. So if you ever are tracking your units, you can remember that a watt is a joule per second. It just falls out of this equation because you calculate power with work in joules and time in seconds. So finally, energy is the ability to do work. Now I'm defining energy in terms of work. It's a little weird because later I'm going to tell you that work and energy are somewhat equivalent. I'll have to be honest, I'm not too in love with this definition of energy. And upon researching this in a lot of different textbooks, I found out, or just realized, that energy is a pretty hard thing to define. It's like one of those things, you know what it is, but you can't really define it. It's hard to define. So I'm going to satisfy myself and hopefully you with this definition. Energy is the ability to do work. Okay? Now, in terms of mechanical energy, which is things of a mechanical nature, I guess, there's two kinds. There's kinetic energy and potential energy, right? Other forms exist. We're not going to worry too much about those yet. We'll get to those soon. And if you want to calculate mechanical energy, you can use these handy equations: kinetic energy 1/2 mv squared, potential energy mgh. And a couple comments on this. Remember that the v is just the magnitude part of velocity, also known as speed, right? Because we're trying to calculate a scalar here, which is kinetic energy. And potential energy, when we talk about height, that is compared to an arbitrary zero reference. So you get to decide where your zero reference is for potential energy. Once you choose that, you need to stay consistent throughout your calculations so that when you get an answer, it makes sense in your coordinate system. Okay, now, those two kinds of mechanical energy can be exchanged with one another. If I drop an object, I'm going to go right off the camera here, and I'm going to pick up an object, and I'm going to come back, and I'm going to drop it. So here I am, dropping the object, boom, right? If I drop an object, I'm converting potential energy, which is the energy of the object sitting here, some h above my arbitrary zero reference. I'll pick the ground here. And I exchange that for kinetic energy. As it loses potential energy, it picks up kinetic energy. As you well know, it speeds up. You can think through, and it's worth thinking through, other examples, like you can think of a ball thrown upwards, you can think of a pendulum. I encourage you to do those thought experiments and think about what they mean with respect to potential energy and kinetic energy. Let's talk about the exchange now between work and energy. I'm going to say loosely you can exchange work for energy. They're somewhat equivalent. Let's take a look at one example here. In this picture, I have a person lifting an object at constant speed. We'll see that's going to be useful later. And if we look at that, we can draw a force diagram, as I do on the right, and you can see that because it's constant speed, thus no acceleration, the force of the hand must be the same as the force of gravity on the object, which of course is mg. So the work done by the hand on the object is equal to the change in potential energy in this case. I emphasize the word by and on. I encourage you to emphasize those two, because sometimes it's easy to get mixed up as to who is doing what onto what object and so on. We'll see more examples of that as we go. So in summary, we've defined three things. Let's take a look at the slide. We've defined work, we've defined power, we've defined energy, and we've written some equations to help calculate those things. Now, I would normally stop here and call this the end of the presentation, but I thought I'd share one other little tidbit with you. I mentioned it's difficult to define energy. In one of the books I searched for, I found this definition. Check this out on the slide here. The canonically conserved quantity corresponding to the absence of explicit time dependence in the Lagrangian. What's a Lagrangian, and what, for that matter, what is time? I just want to use this as an example of, number one, maybe reading over your head. Honestly, I can't describe why that makes sense to the author of this book. This is Richard Muller's The Physics of Time. It's called Now, is the name of the book. I recommend it. I've read it, and I am trying to understand, what is time anyway? It's kind of weird. It's one of those things where you think about it and you think you know what it means until you try to define it. That's pretty much what this book is about. While I am pitching books, here's another one relating to time. This is Stephen Hawking, well-known physicist. And finally, this book, one of my favorites, it's called Energy for Future Presidents. This is also written by Richard Muller. And since we're on the topic of energy, I thought what better time to recommend this favorite book to you. So there is the end of my book recommendations, and that is all I have to say about work, power, and energy for today.